Hello everyone and welcome back to the C++ 3D game tutorial series. In this 7th episode, we will see how to work with vertex and pixel shaders and how to use them to render a colored quadrilateral. As always, we will face three main parts: the requirements, design, and implementation of all the software components required to render a colored quadrilateral. Let's start with the requirements. We need a C++ IDE. In this series, we use Visual Studio 2022 Community. The target platform is Windows. The target graphics API is DirectX 11. And last but not least, a good understanding of the C++ programming language is recommended. Now we can start the design part. In the previous episode, we learned how to render our very first triangle on the screen. We covered how to create a vertex buffer to manage the triangle's vertices and how to define an input layout to tell the GPU how to interpret the vertex data structure written in C++. We also extended the vertex and pixel shaders to properly process the triangle's vertices and apply color to its surface. This time, we are going to focus on rendering a new type of geometric shape, a quadrilateral. This will lead us to extend the vertex and pixel shaders created in the previous tutorial. We will also learn how to reflect changes made to the vertex data structure into the input layout automatically, without having to manually update the layout each time. Let's begin by diving deeper into the concept of a quadrilateral. At its core, a quadrilateral, just like a triangle, is a type of polygon made up of vertices. As we have already learned, a triangle consists of three vertices. This time, however, since we want to render a different kind of polygon, we need to create a different list of vertices. So what vertices do we actually need in order to render a quadrilateral? That depends on the primitive topology we set in the graphics pipeline. The primitive topology tells the GPU how to interpret the list of vertices, which we provide through the vertex buffer, in order to form geometric shapes such as points, lines, or triangles. We can choose between different types of primitive topologies: the point list, where each vertex is rendered as a separate point; the line list, where every pair of vertices forms a line; and the triangle list, where every group of three vertices forms a separate triangle. There are other options too, but for now, these are enough to grasp the basic idea. For rendering our quadrilateral, the most suitable primitive type is, of course, the triangle. So, we need to find a way to create a quadrilateral using triangles as our base. The simplest way to do this is by combining two triangles together. Let's use the triangle list topology to achieve this. As the name suggests, the triangle list topology works by placing groups of three vertices one after the other in sequence within the vertex buffer. These groups represent individual triangles. In the diagram, we can see two such groups, one in red and one in blue, each forming a triangle. In this way, we effectively create a list of triangles. Since each triangle requires three vertices and we need two triangles to build a quadrilateral, we will need a total of six vertices. Just like before, we will use normalized device coordinates, often referred to as NDC, to define the positions of these six vertices. If we look at the image, we can notice that some of the vertices overlap. For instance, vertex 2 and vertex 3 occupy the same position, as do vertex 0 and vertex 5. If we examine the vertex list closely, we can confirm that these overlapping vertices do indeed share the same coordinate. Another important detail is the order in which we list these vertices. By default, Direct 3D11 renders the front face of a triangle only when its vertices are defined in a clockwise order. So, in our case, for the first triangle, the red one, the vertices should be ordered from the bottom left to the top left, and then to the top right. In other words, from vertex 0 to vertex 1 to vertex 2. Of course, we could also go from vertex 1 to vertex 2 to vertex 0 and so on, as long as the order remains clockwise. If we define the vertices in a counterclockwise order, say from vertex 2 to vertex 1 to vertex 0, the front face of the triangle will not be rendered. This concept is known as the winding order of a triangle. This order determines the triangle's facing direction, front or back, and is crucial for operations like backface culling. We can adjust the winding order by configuring the rasterized state, but for now the default behavior works well for us. Once we have correctly defined the positions of all 6 vertices, our quadrilateral is geometrically ready. At this point, we want to color the surface of our quadrilateral in a specific way. Each corner should have a different color, which will result in a smooth gradient across the surface. To do this, we need to define a proper structure for our vertex type. In the previous episode, our vertices only contained position data, so we didn't need to define a custom structure. We just used a simple three-dimensional vector to create the list of positions. But now that each vertex needs to hold multiple attributes, specifically both position and color, we must define a structure for our vertex type in C++. This structure will be used to build our vertex list. We also need to reflect this new vertex structure in our HLSL shader code. We will do this by defining a structure, typically called VS input. As the name suggests, this structure represents a single vertex that is passed as input to the vertex shader. But that's not all. We also want the color data to be accessible in the pixel shader, so that it can use the color information to shade the surface accordingly. Right now, our vertex shader only returns the clip space position of each vertex. But in order to pass the color along too, we will need to define another structure in HLSL, which we will call VS output. In the VS output structure, we will include 2 attributes, one for position, labeled with the semantic SV position, which represents the position in clip space, and another for color. This way, the color attribute can travel through the entire shader pipeline. Inside the vertex shader function, we process the input data and assign the appropriate values to a VS output object, which we then return. Then, in the pixel shader, we simply define a parameter of type VS output, which receives the output of the vertex shader. And once the pixel shader receives this data, it reads the color and returns it, successfully shading our quadrilateral with a smooth gradient. Before we can render the final quadrilateral, there is one more step. We need to reflect the changes we made to the vertex shader input structure in HLSL into the input layout elements that are manually defined in the graphics pipeline state class. Previously, our input layout only included the position attribute. Now, we will also add the color attribute to match our new vertex structure. Once all these steps are completed, we should see the final result, a properly rendered quadrilateral with smoothly blended colors at each corner. As a final improvement, we will automate the creation of the input layout so that we don't have to manually update it every time we change the vertex shader input structure. We will do this by using a key Direct 3D11 API function called d3dreflect. The purpose of D3D Reflect is to extract metadata information about the attributes defined in the vertex shader input structure directly from the compiled shader bytecode. Thanks to this function, we will be able to freely update the vertex shader input structure inside the HLSL code without needing to manually adjust the input layout ever again. If you have any questions, doubts, or comments about this episode, feel free to leave them in the comment section of this video or on the Discord server. You can find the link to the Discord server in the video description. Also, if you find these tutorials helpful, please consider supporting their development on Patreon. Every contribution makes the difference, no matter the amount. Great! We have gathered all the necessary information to start the implementation. Let's start by creating a file for our shader. To do this, we first need to create an assets folder inside the DX3D directory. This folder will contain all the assets required by the DX3D engine. Today, we are going to add a shader file, so let's create another folder inside Assets and name it Shaders. Now, inside the Shaders folder, let's add a new shader file. Click on Add New Item, then choose HLSL from the available item types, and a list of shader templates should appear. Let's click on Vertex Shader and name our file Basic. At this point, the basic.hlsl file should appear inside the shaders folder. Before we move on, it's important to right-click the shader file and choose Exclude from Project. If we don't, Visual Studio will try to compile it automatically. Since we handle shader compilation ourselves, we don't need the IDE to do it. Now we are ready to copy and paste the shader code we wrote in the previous episode to render our first triangle into the basic HLSL file. Let's head over to the graphics engine C++ file. Inside the constructor, find the shader code and copy it into our basic file. Before we proceed further, it's important to enable the HLSL Tools extension in Visual Studio so we can enjoy syntax highlighting and IntelliSense support for HLSL files. To do this, click on Extensions in the menu bar and select Manage Extensions. The Extensions Manager tab should appear. Here we will see a list of all available extensions for Visual Studio. In the search box, let's type HLSL to find the HLSL Tools extension. If it is not already installed, click on Install. It's a good idea to also check the Installed tab to verify whether it's already available. Generally, HLSL Tools is enabled by default in Visual Studio 2022, but if not, go ahead and install it. Once that's set up, go back to Graphics Engine C++ and we can now start working on loading our shader file content so we can pass it to the compile shader function. First, we need to define the shader file path. Let's use a relative path to locate the basic.hlsl file. A file path tells the system where a file is located, similar to a detailed address. There are two main types of file paths. The absolute path is a full path starting from the root of the file system, like the C drive on Windows. The relative path starts from the current working directory, where the application is running. In Visual Studio 2022, relative paths are relative to the root of the project folder. In our case, that's the DirectX game folder. So we can write the path starting from the DX3D folder, then go into Assets, then Shaders, and finally access the basic.hlsl file. Now, how do we open that file and read its content? Luckily, C++ provides a useful class for working with files. IF stream. Since we only need to read the contents of the shader file, we can use the ifstream input file stream class. To use it, we must include the fstream header file. ifstream allows us to open a file for reading. We pass the shader file path as a parameter and the file is opened in read mode. However, we should check whether the file actually opened correctly. We can do this with a simple if statement using the not operator on the shader stream object. If it fails, we can log and throw an error using the x3d log throw error and display a message like failed to open the shader file. Once we know the file opened successfully, the next step is to retrieve its data. To do that, let's use the standard C++ string class, which is designed to manage array of characters. We will use brace initialization to create a string and load the file contents using the range constructor. This constructor takes two iterators, one pointing to the start of the file and one to the end, and copies everything in between. We will dive deeper into iterators later, but for now, let's create an iterator pointing to the beginning of the file using iStreamBuffIterator. Then let's create the end iterator with iStreamBuffIterator again. This process copies the entire content of the shader file into the shader file data stream. Think of iterators like pointers. One marks the beginning of the file, the other the end. When we call the string's range constructor, it loops from the start to the end and copies each character into the string. Great! At this point, we have our entire shader code stored in a string. We will reuse the shader source code variable and assign it the pointer to the internal character array of the shader file data stream by calling the cstream method. Next, let's remove the old shader source name variable and replace it with shader file path. Now, let's define shader source code size by retrieving the length of the string using the length method. Last but not least, let's make sure to replace every use of shader source name with shader file path. Now, let's test if everything works correctly. Perfect, everything seems to be working as expected. Let's now try modifying the basic.hlsl file a bit. For example, we can change the triangle's color to green by returning a float 4 in the pixel shader, with the red and blue channels set to 0. And there we go, our green triangle appears. Let's now reset the triangle's color to the original. The next step is to render a different kind of shape. Let's start by rendering a quadrilateral. As we have seen in the introduction, a quadrilateral is essentially a polygon made up of two triangles. To render it, we simply need to add 3 additional vertices to the vertex list. First, let's slightly adjust the positions of the original 3 vertices which represent the first triangle of the quadrilateral. Then, let's add the next 3 vertices which will form the second triangle that completes the quadrilateral. Let's remember that we are currently rendering the list of vertices in triangle list mode, where every group of 3 consecutive vertices represents one triangle. let's check if it works. Great, everything seems to be rendering correctly. What's next? Let's take a deeper dive into the usage of shaders. This time, we want to color the surface of our quadrilateral. Specifically, we want to render each corner of the quadrilateral with a different color. Since each corner corresponds to a vertex, we will need to assign a unique color to each vertex. To do this, as mentioned in the introduction, we need to define multiple attributes for each vertex. Currently, our vertices are defined only by their position, which is a three-dimensional vector representing the normalized device coordinates, or NDC. That's why our vertex list is currently an array of three-dimensional vectors. Now we want to add another attribute, the color, to each vertex. To define multiple attributes for each vertex, we need to use a structure. So let's go to the graphics engine header file. Inside the graphics engine class, let's define a new structure called vertex. Inside this structure, let's add two attributes, a vec3 to represent the position, and a vec4 to represent the color. Of course, we will need to include the appropriate header files for both types. We use a four-dimensional vector for the color to define the red, green, blue, and alpha channels. We are now ready to use this structure to define our new vertex list. IntelliSense will likely highlight that we need to adjust the brace initializers. In particular, each vertex object now requires two separate initializers, one for the vec3 position, which we already have, and one for the vec4 color. Let's start by setting the color of the first vertex to red. For the second vertex, let's set the color to green. For the third vertex, let's use blue. Now we need to define the colors for the second triangle. The first vertex of the second triangle is shared with the third vertex of the first triangle, so we can reuse the blue color. The second vertex of the second triangle, which represents the bottom right corner of the quadrilateral, is unique. Let's assign it a purple color by setting both the red and blue channels to 1. The last vertex of the second triangle is the same as the first vertex of the first triangle, so we will assign it the red color again. At this point, we have defined the complete vertex list for our final quadrilateral. Now we need to reflect these changes in the shader source code. Let's open the basic.hlsl file. The first thing we need to do is define the input data that will be passed to the vertex shader. Previously, since each vertex only had position data, we passed a three-dimensional vector to the vertex shader. Now we also want to pass the color information. To do this, we need to define a structure in HLSL. Let's call it VS_input, which stands for vertex shader input. Inside this structure, just like we did in the C++ vertex structure, we need to define the vertex attributes that would be passed into the vertex shader. Keep in mind that the structure defined in HLSL must match exactly the structure in C++, or else the data will not be interpreted correctly by the GPU and the mesh will not be rendered as expected. In HLSL, a vector of three float values corresponds to a type called float3. As we saw in the previous tutorial, every input attribute in a shader must use a semantic. A semantic is a label that tells the GPU what the variable represents and how it should be used in the graphics pipeline. Without this semantic, the GPU wouldn't know how to interpret the input. For the position, we will use the semantic called position, and we can assign it the index 0. For the color, which is a 4 float vector, we will use the float 4 type and assign it the color semantic with the index 0. Now, in the vertex shader function, let's replace the previous single position parameter with our new VS input structure. Let's call the input parameter simply input. At this point, we need to return more than just a position for the vertex shader. We also want to pass the color data to the pixel shader, so it can render each corner of the quadrilateral with the correct color. To do that, we need to define another structure called VS output, which will contain all the data returned from the vertex shader. The first attribute inside VS output will be the position, but not just any position. It must be transformed into clip space, which we've discussed in earlier tutorials. To specify a clip space position, we need to use the semantic SV position. The prefix SV stands for system value, indicating that this is a built-in semantic required by the GPU pipeline. Vertex shaders are only allowed to return position values using this semantic. Next, we add the color attribute to the output. Here, we can reuse the same semantic as before, color with index 0. Once these attributes are returned from the vertex shader, they are processed by the graphics pipeline and passed to the pixel shader, which uses them to color the surface of the mesh. We are now ready to create and populate a VS output object inside the vertex shader. As we would do in C++, let's initialize an object called output and set its position using a float 4 value that wraps the position from the input structure. We then assign the color attribute of the output using the color from the input. Finally, we return the output object. Since the same structure returned by the vertex shader is used as input to the pixel shader, let's define the VS output structure as the input parameter of the pixel shader function. At this point, we can simply return the color attribute from the input to produce the final color on the screen. Lastly, we need to reflect the structure of the input vertex data in our graphics pipeline state. Let's copy the attributes of the VS input structure and then go to the graphics pipeline state C++ file. We can paste the attributes before the input element array and comment them for clarity. Previously, we only defined the position attribute in the input layout. Now we also need to define the color attribute. Let's add a new input element with the semantic name color, semantic index 0, and the format R32, G32, B32, A32 float, which represents 4 float values. The input slot remains 0 since we are using a single vertex buffer, and now we must define the align byte offset. Since the color attribute comes immediately after the position attribute, and the position consists of 3 floats, each float being 4 bytes, the offset will be 12 bytes. The input slot class remains set to per vertex data, and the instance data step rate is 0. Let's run the application and see if everything works as expected. Awesome! We have successfully rendered a quadrilateral with each corner having a different color. To wrap up, let's improve the background color a bit. Go to the graphics engine C++ file and in the render method, change the color passed as a parameter to the clear and setback buffer function. So far, so good. The problem we are facing now is that manually reflecting the changes made to the input vertex data structure in the HLSL file into the input layout defined inside the graphics pipeline state each time is not very feasible. Also, we might end up working with different vertex shaders, each defining its own unique input layout. In such cases, relying on a single hard-coded input layout is no longer a suitable approach. To solve this issue, we need a way to analyze the shader source code, retrieve its metadata related to the input vertex structure, and use that metadata to automatically generate the final input layout. This process is commonly referred to as reflection. We can achieve it using the d3d reflect function provided by the Direct3D API. So, as a first step, let's create a new class and name it Vertex Shader Signature. As the name suggests, Vertex Shader Signature will be responsible for handling the compiled binary of a vertex shader and providing all the metadata needed to generate the input layout dynamically. As always, let's wrap this class inside the DX3D namespace. Let's make the class final and extend it from graphics resource class, including the appropriate header file. We are now ready to define the constructor and pass a graphics resource descriptor as a parameter. With that completed, let's move on to the implementation. Of course, let's also clean up the auto-generated include directives. Let's call the constructor of the base class and pass in the descriptor parameter. The first thing we need to do now is call the d3d reflect function. To use it, we need to include the d3d compiler header file. d3d reflect is a function from the Direct3D 11 API that allows us to extract metadata from a compiled HLSL shader. It enables us to inspect various shader components at runtime, such as variable, constant buffers, and input-output signatures. For now, let's focus on the input signature of the vertex shader. Like most Direct3D functions, D3D Reflect requires a few parameters. The first two are a void pointer to the shader binary data and the size in bytes of that data. So we need a way to pass the compiled vertex shader binary to the vertex shader signature class. Let's go to the common header file and define a new structure named vertex shader signature descriptor. Inside it, we will define a constant smart pointer to a shader binary and call it VS binary, where VS stands for vertex shader. A key point here, since we want vertex shader signature to take ownership of the past shader binary, we will define a smart pointer and not a non-null reference, just like we have done in previous tutorials. Now let's return to the vertex shader signature header file and update the constructor to take a vertex shader signature descriptor as a parameter. Let's also define a shader binary pointer attribute inside vertex shader signature. This way, we maintain ownership of the shader binary. Now copy and paste the descriptor parameter to the implementation file. At this point, let's begin the implementation. First, initialize the vs binary attribute with the vs binary from the descriptor. Then we should check if the passed shader binary is null. If so, let's log and throw an invalid argument exception with the message no shader binary provided. Next, we need to confirm that the passed binary is actually a vertex shader, since the purpose of this class is specifically to handle vertex input data. If it is not a vertex shader, we throw another exception with an appropriate message. Alright, now we can retrieve the raw shader data by calling the getData method on the binary object. What we need now is to pass this data and its size to the d3d reflect function. The third and fourth parameters of d3d reflect define the output, which is the interface we will use to reflect shader information. To handle this, let's go to the vertex shader signature header file and add a com pointer to a d3d11 shader reflection interface. Let's name it shader reflection. Back in the C++ file, we will pass this using the AND operator through the iidppvargs macro. As with many D3D11 API functions, D3D Reflect returns an H result, so we will use our DX3D graphics log throw on fail macro to handle errors properly. Once the shader binary has been successfully reflected, we can call the getDesc method on the shader reflection object to retrieve the shader's description. This method requires a pointer to a D3D11 shader desk object, so let's define and pass that. Again, we will use our macro to check for errors. We are now ready to call the most important method in this process, getInputParameterDesc. As the name suggests, this method returns information about each input parameter in the vertex shader, which is exactly what we need to create our input layout. The first parameter is the index of the input parameter, but we currently don't know how many parameters there are. To get that number, we use the input parameters attribute from the shader description object we just filled. Let's also store this number in the header file by adding an attribute called num_elements of type unsigned integer. Good, what's next? We need to loop over all input parameters and retrieve the available metadata. Since we are using C++20, we can take advantage of a modern approach to iterate over a numeric range. Let's include the range's header file. Then we create a for loop using IOTA, which generates a lazy sequence of integers from 0 to, but not including, num elements. We will define the loop variable as auto_i and use 0u as the starting value to explicitly denote an unsigned integer. Inside the loop, we will need to pass I as the index parameter to the getInputParameterDesc function. The method also requires a pointer to a D3D11 signature parameter desk object. Since we will be handling multiple parameters, we need to define an array of D3D11 signature parameter desk objects. Let's define this array outside the loop and call it params. We also need to define its size. While a dynamic vector will normally be used, D3D11 supports a maximum of 32 vertex input elements for the vertex shader, so we can safely define the size as 32 using predefined macro D3D11 standard vertex element count. Inside the loop, we will pass a pointer to the appropriate element in the params array to get input parameter desk function. And as always, we will check for errors using our log throw on fail macro. Last but not least, we are now ready to automate the creation of the input elements array, which we have been defining manually in the graphics pipeline state class. So let's go to the vertex shader signature header file and define an array of D3D11 input element desk objects called elements. We will use the same macro for the size, that is, D3D11 standard vertex element count. Back in the implementation file, we can loop over the params array and fill in the elements array accordingly. To guide this process, let's revisit graphics pipeline state C++ file, copy the manually defined input elements array, and paste it just before our loop as a comment. As we can see, from now on, the generation of this array will be completely automated. As the first attribute, we use the semantic name. Then we need to specify the semantic index, followed by the dxgi format. Unfortunately, the input parameter descriptor doesn't directly provide this format information, so we need to compute it using the provided data. To handle this, let's go to the graphics utils header file and add a new inline function within the graphics utils namespace. We will call it get the XGI format from mask. To determine the XGI format, we need to provide two values. The first is a value of type D3D register component type, which we can name type. This indicates the underlying scalar data type used by the components of the parameter. By components, we refer to values such as x, y, z, and w. For instance, if the HLSL attribute is a float4, this type will represent float. The second required value is an unsigned integer called mask. This mask provides a bit pattern indicating which components are active in the attribute. For a float4, all four components x, y, z, and w are present and the corresponding bits will be set. Since we are using Direct3D specific definitions, let's include the D3D11 header file. Now we need to determine how many components are used by the input parameter. We can extract these from the bit mask. To explain briefly, a bit mask is a sequence of bits used to represent or manipulate specific data. In our case, the mask tells us which components among x, y, z, and w are used. If the x component is used, the first bit is set to 1, otherwise it is 0. If y is used, the second bit is 1, otherwise 0. This continues for z and w. So for a float3, the bit mask will have 3 bits set to 1. For a float4, all 4 bits will be set. To count the number of bits that are set to 1, we perform a bitwise operation. Fortunately, C++ provides a standard function for this that is called pop count, which counts the number of 1 bits in an integer. To use it, we include the bit header file. Next, we check if the number of components is less than 1. If that's the case, there is clearly something wrong, so we return the XGI format unknown. Once we have handled that, we can define a format table of type the XGI format. This is essentially a matrix, an array of arrays, where each row corresponds to a data type, for example, integer, unsigned integer, float, and each column corresponds to the number of components. To simplify things for now, we will add support only for float types. We will initialize the table using brace initialization and provide a sequence of the XGI formats. The XGI formats are 32 float for a single X component, R32 G32 float for X and Y, and so on up to 4 components. We are now ready to return the correct DXGI format from the table. Since we only support float for now, we set the first index of the format table to 0. The second index is determined by the number of components minus 1. To be more precise, let's define a type index variable, initialized to 0 to represent the float type. We will use this as the row index in the format table. Let's also add a switch statement to handle the type parameter. If the type is D3D register component float32, we keep type index as 0. For all other types, we return for now the XGI format unknown. That's it. Now let's go back to the vertex shader signature C++ file and include the graphics utils header. We can now compute the DXGI format by calling the getDXGI format from mask, passing in the component type and the mask obtained from the input parameter. As usual, let's set the input slot to 0. For the aligned byte offset, we need to compute the size in bytes of each input parameter. Fortunately, D3D11 provides a helpful macro for this, D3D11 append aligned element. As the name suggests, this macro allows us to let Dir3D compute the correct offsets automatically by appending each consecutive element. Then we pass the input classification, which is D3D11 input per vertex data, and finally the instance data step rate, which is 0. We have now completed the reflection process of the vertex shader binary. Next, let's go to the graphics device header file and add the create vertex shader signature method. As always, this method will return a shared pointer to the resource. So let's go to the core header file, forward declare the vertex shader signature class, and define a type alias for the shared pointer, as we have done for other resources. Alright, let's return to the graphics device header file and finalize the method signature. At this point, we can implement it. As usual, we will use the makeShared function to create a shared pointer to a vertex shader signature object. We will pass the required descriptor and, at the end, include the vertex shader signature header file. So far, so good. Next, let's go to the graphics engine C++ file, call the create vertex shader signature method, and pass in the vertex shader binary. Now comes the part where we need to pass the signature to the graphics pipeline state. So let's open the common header file And in the graphics pipeline state, the script structure replace the type of the VS attribute to be vertex shader signature. Now we can move to the graphics pipeline state C++ file and finalize its logic. Inside the constructor, we no longer need to perform the vertex shader validation, since this is already handled by the vertex shader signature class. So we can safely remove that check. Next, we need to retrieve the shader binary data, just like we did before. However, this time, the vertex shader binary is encapsulated within the vertex shader signature class. So we need to add a method to expose that data. Let's go to the vertex shader signature class and add a get shader binary data method. It should be marked const no except, since it doesn't change the state of the class or throw exceptions. Let's also rename the structure currently used to store shader binary data. Since this structure can be reused for any type of binary, we will rename it to binary data. Be sure to reflect this change in the shader binary class as well. Once that's done, we can finalize the getShader binary data method. It simply returns the result of calling getData on the shader binary object. Let's return to the graphics pipeline state C++ file and retrieve the vertex shader binary data using this method. Now, finally, we can replace the previously hard-coded list of input elements with the dynamically generated one stored inside the signature object. We do need a way to access it, so let's go back to the vertex shader signature class and add a method named getInputElementsData. It should return a binary data and also be marked const no except. To implement it, we simply return the internal elements array and the num elements value. Now we can go to the graphics pipeline state C++ file and retrieve the vertex shader input elements. Let's remove the hard-coded array and instead pass the data from the new dynamically generated list. Since binary data provides a generic void pointer, we need to cast it to the correct type using static cast. In this case, the type is D3D11 input element desc. And that's it, we are almost done. Let's place a breakpoint in the graphics pipeline state constructor and another one in the vertex shader signature constructor. In the end, let's go to the graphics engine C++ file and remember to replace the vertex shader pointer passed to the create graphics pipeline state method with the new signature object. Let's also add an additional breakpoint in the graphics engine constructor. We are now ready to compile and debug everything. First, we retrieve the shader code from file and then use it to create the vertex and pixel shader binaries. At this point, we begin creating the vertex shader signature. In its constructor, we first check if the shader binary has been provided. Then we verify if the binary corresponds to a vertex shader. And once that's done, we perform reflection on the binary to extract its metadata. We retrieve the actual number of input elements along with the details of each input parameter. And finally, we generate the list of input elements that will be used to create the input layout within the graphics pipeline state. As we can already see from IntelliSense, the input elements list containing the position and color attributes used by the basic HLSL shader is now correctly generated and handled automatically. Now that the vertex shader signature is ready, we can proceed to create the graphics pipeline state. Here, we gather all the required data and use the generated input elements list to create the input layout. As before, we then create the vertex and pixel shaders. And here it is, the final result. That's all for now, folks. Today we learned how to improve and better manage shaders and how to generate the input layout automatically. We saw how to create a shader source code file and how to retrieve its content programmatically. We also create a quadrilateral mesh made up of two triangles using more complex vertices that include both position and color data. We then explored how to extend both the vertex and pixel shader code to correctly process these complex vertices and render the colored surface of the quadrilateral. Finally, we looked at how to automatically generate the input layout required by the graphics pipeline using a very useful function called d3d reflect, which allowed us to extract all the necessary information directly from the shader bytecode. Next time, we will explore how to create animations using a constant buffer. Hope you enjoyed this episode. See you soon. Thank you for watching.